we are denoting it by A. Now, if we look at the entire situation, we find that in quadrilateral AMDN, angle AMD plus angle AND is 180 degree. Now, that means AMDN is a cyclic quadrilateral. Hence, the sum of opposite angles, that is A plus pi minus R1 plus R2, will be also 180 degree, and that gives me a relation which is to be remembered, that angle of prism is equal to sum of R1 and R2. R1 is angle of refraction at first interface and R2 is angle of refraction at second interface. In fact, we can call it either angle of incidence or angle of refraction, because the path of light rays is reversible. Now let's find the deviation suffered by ray as it is passing through the prism. Now at the two interface, the incident ray is rotating clockwise, and we can see it is very clear from the figure that the deviation at first interface, that is delta 1, is I minus R1. And similarly, it is clear from the figure that the deviation at the second interface is E minus R2. And these two deviations are in same sense, as the total deviation suffered by ray passing through the prism is delta 1 plus delta 2. That is I minus R1 plus E minus R2. And on simplification, we get deviation as I plus E minus A, using the previous equation that A is equal to R1 plus R2. Now, this expression for deviation can also be worked out using the geometrical consideration. We can see that exterior angle in a triangle is always equal to opposite interior angle. Now here you can see very clearly the total deviation delta, that is the angle between incident ray and final emergent ray, is forming exterior angle, and I minus R1 and E minus R2 are forming interior angle. So that way also we can get the expression for deviation. Now we would like to trace a graph between deviation versus angle of incidence. Obviously, the expression for deviation as a function of angle of incidence is not simple. Now, by using Snell's law, we can substitute the value of angle of emergence in the equation, and that gives me finally the expression for deviation as a function of angle of incidence, which is shown on the screen. Now it's really horrifying looking at this equation, and if somebody asks you to trace the graph, it will be much more difficult. Now we have done laboratory demonstration where we are asked to draw graph between deviation versus angle of incidence. One thing is very sure, it is a non-linear function. If we just analyze mathematically a bit, we find that this function will have a minimum value, that is, there is one angle of incidence for which deviation is minimum. Going by mathematical analysis, we find the graph between deviation and angle of incidence will be approximately as shown on the screen. Please have a careful look at the graph. We see that initially as angle of incidence is increased, deviation is decreasing, becoming minimum, and thereafter increasing continuously. Now there are few things that we have to remember about this graph. That this graph may resemble like parabola, but it is not parabola. Definitely we have seen the equation just now. It is a very complicated equation involving inverse function. So it is a unsymmetrical graph. That is the second point we have to note, that the graph is unsymmetrical about angle of incidence at which deviation is minimum. Now let's move into many more details of this triangular prism. First we take up the condition of minimum deviation. Now we know from calculus that whenever a function is minimum or maximum, its first derivative is 0. Now here deviation is a function of angle of incidence. So if we differentiate with respect to angle of incidence and we equate d delta by di is equal to 0, so we land up in result which we call it condition for minimum deviation. Now the condition for minimum deviation is that angle of incidence will be equal to angle of emergence, that is one thing, and R1 will be equal to R2, and as we know that R1 plus R2 is A, therefore we can write R1 is equal to R2 is equal to A by 2. Now we can write the value of minimum deviation. So I am using the subscript m denoting the minimum. So delta m will be twice I minus A. As I said earlier, in condition of minimum deviation, angle of incidence will be same as angle of emergence. Now applying Snell's law at any interface. Let's take up the first interface. I can write from Snell's law, surrounding medium is air, 1 into sin I is equal to mu sin R1. Substituting the value of I and R1, we get the expression for refractive index, and it is equal to mu is equal to sin of A plus delta m by 2 bracket close whole divided by sin of A by 2. Students are supposed to remember this unique relationship which is valid in the situation of minimum deviation.